Right, so I make it 5:30, so let's get started. So again, good morning, everybody. Thank you for joining the short paper session on perception representation. So I'm the session chair, Anjana, and our first presenter for today will be Zack, who will be talking about his work, Dark Mode or Light Mode, exploring the impact of contrast polarity on visualization performance between age groups.
Thank you. So let me the screen share going. Okay, cool. On behalf of myself and my advisor, I'll be presenting dark mode or light mode, exploring the impact of contrast polarity on visualization performance between age groups. So there's two kind of main motivations for this work. The first is the kind of focus group in case of my research, people in late adulthood, often referred to as older adults. So this is a group that's not very well represented in VIS research. It's also a very noticeably growing population. There are a lot of changes that are associated with aging, both physiological and like more sociological, that can affect the way that we interact with and use and understand data visualizations. And this is also a group among the rest of the population that's increasingly using visualizations. They can be used to track health, like when you're looking at the weather or making like a major financial decision. So this is a group that needs more representation in research, and this is my kind of main area of interest. This is also about contrast polarity. So for giving a brief idea of what this is, this is often referred to colloquially as like light mode or dark mode. So you have positive contrast, and that's like a dark object in the foreground on a light background. Then you have negative contrast, which is a light object in the foreground on top of a dark background. Some research switches those terms, but this is the way that we'll be using them here. And so this is an area of research studying contrast polarity that has some existing work and just more general like reading. Positive contrast has been shown to help with like proofreading, whereas there's been some research with age-related stuff about the way that like older adults use or like view dark mode as something that helps like reduce eye strain, whereas younger folks viewed as more like an aesthetic choice. So there's some research in terms of reading, just like text, but not in terms of data visualization. And in general, this is something that's coming up a lot more in user interface design. You can see it on like websites, on Discord, on your phone. There's often a choice of do you want to have it in light mode or dark mode, among other kind of color modes as well. So in order to kind of see how age interacts with this notion of contrast polarity, we ran a study. So it was an online study. We recruited, after filtering, 52 younger adults, referred to as YA, and then 52 people in late adulthood, PLA, which we filtered as age 60 or older. We got the software from Sarvghad et al. From their 2018 paper, modified it slightly, which we'll see in a moment. This paper generally, the format is they'll present you with a visualization and a question, and the question will have 4 multiple choice answers, and you have to answer that question. So the stimuli, there were 6 kind of possible combinations. So we had 3 types of visualizations. This was a subset from the original paper. And then 2 possible contrast polarities, positive and negative. For each of those combinations, then someone would see 4 different data sets and 4 different questions depicted using that data set. So there's a total of 24 stimuli that a person would see. One person might see the light mode version of chart number 1, whereas another person might see the dark mode version of that. So the total like questions were the same per person, but which one they saw, positive or negative contrast, varied. So essentially had them fill out a questionnaire. They did some practice questions to get familiar with the format. And then we would show them or have them go through 12 questions for one type of polarity and then 12 for the other. Whether it was negative and positive or vice versa, was randomly chosen per person. We then, as they were doing this, we would measure their accuracy and time. So as far as how we kind of try to quantify how contrast polarity impacted their performance, we use something called percent differences. Essentially, if you take one value, say their mean accuracy with positive contrast, then that same person's mean accuracy with negative contrast, so 2 different values, you can take the absolute value of their difference and divide it by the mean of those 2 values. And that gives you a kind of quantitative way of seeing how much of a difference there are between the 2. And this can be compared with other values calculated in the same way, kind of across different scales. So we're going to kind of quickly combine results and takeaways. So the one question we had was, does the impact of contrast polarity change much with age? Right. So was there more of were there larger percent differences for PLA or smaller differences compared to the younger group that we had? So this is one of the figures in the paper. We'll focus for now on the contrast polarity section. Orange is young adults and black is PLA. And you want to look at just comparing for each accuracy and time, just the stuff within each little box. We did more detailed analysis in the paper, but essentially if they overlap a lot, then there's very little difference. And if there's no overlap between these bootstrapped ranges, then we would say that there's likely to be strong evidence of differences. So here we see a lot of overlap between our ranges of the percent differences per person. So we kind of concluded that there was not much of a difference with age, just due to contrast polarity itself, both for accuracy and time. We also want to see, comparing contrast polarity, which is like a non-data encoding, to something like visualization choice, which is a data encoding. So essentially, instead of swapping the contrast polarity for percent difference, we essentially did it for every visualization type in the study, and then kind of averaged them all together. And what we found was that in this case, we wanted to kind of compare like colors to each other to look for overlaps. And what we found was that for accuracy, there was no overlap for either age group. So there was a strong evidence of a difference. Whereas for time, there was very little overlap. So essentially, we could conclude that contrast polarity seems to impact time as much as visualization type, but that's not the case for accuracy. Another question we had was, does one of the contrast polarities have more of a noticeable impact on performance? In other words, larger percent differences. So what we found comparing these two charts here is that, first of all, we took everyone's best performing polarity and kind of grouped them by that, and then took the averages to kind of bootstrap these confidence intervals. And you can see here there's very high overlap between the two ranges. So essentially, we concluded that there was essentially each polarity can give similar improvements for someone. And lastly, we want to see, do people's preferred polarity kind of give them better performance? So we asked them what polarity they use on devices they have, and compared that to how they did for each polarity in the study. So there's kind of a lot going on here. The main thing of note is that if you see an asterisk on a bar, that's the number of people whose polarity matched, who did best with the polarity, and that matched their preference. And what we overall see is that most commonly there are more people who didn't match than people who did match their preference. So in other words, preference didn't really seem to match preferred polarity, which we thought was interesting. So as far as future work, further investigation into this whole notion of contrast polarity, there's a whole lot of other studies that can be run in this kind of realm. And also just looking at other non-data encodings, like using grid lines, which we have a paper later in the session that'll be talking about that in some way, which I'm excited for. So yeah, so that's all I have. And if there's any questions, I can try to answer those.
Great, thank you. So I see a couple of questions on Slido. So one is,
Sure.
did taking the absolute value wash out the polarity of the differences? And did you correct for taking equal physical contrast?
So the first question, did the absolute value wash out the differences? From what I recall, there's a paper that we cite in the paper that talks about the benefits of using the absolute value in this, and using that as the percent difference. I suppose the positive of using the absolute value would be that it's order in it's agnostic to order, right? So it doesn't matter if you did the larger one first or the smaller one, right? So I would say is the main benefit of that. So I mean, there could be negatives to this approach as well, but I think that was one of the kind of main, from what I recall, kind of main benefits of doing that. But there could be other I suppose negatives to using the absolute value. We also
Okay.
did try to filter by people who did best with one and worse with the other, to try to get more of a kind of different spatial kind of feel for that. So they may have also tried to get around the positive negative issue.
Mhm. Cool. I see another couple of questions. I'd suggest continuing
Sure.
that on Discord given
Certainly, yeah.
time. Yeah.
Sounds good.
Thank you. So moving on to our next presentation. So it's Science in a Blink, supporting ensemble perception in scalar fields, presented by Khairi.
Great, thank you very much. Let me go ahead and share my screen. Okay. All right. Well, thank you. Um, this is a talk about scalar fields and quantitative maps, which are pretty ubiquitous in science and often used to communicate critical data. Like you see them being used to show things like hurricane projections or data about the climate crisis, which makes them important to study empirically. And there has been quite a bit of work to try to sort of measure the perceptual affordances of these representations in various tasks. So studies have looked at things like extracting point estimates at specific map locations or detecting small features in field. These are useful studies and very useful information. However, you'll notice most of them are about extracting specific pieces of information from parts of the display. Which begs the question of what happens when tasks require more holistic and quick judgments about entire displays rather than a single feature within one visualization. And this happens when a scientist or even a casual viewer is looking at trying to compare alternative data sets or different simulation runs. And here the goal is often to try to get the gist of the visualizations, at least initially. Now, we know that the visual system can quickly summarize the gist of scenes often in less than a second. So, for example, if I give you this image here, you've probably already concluded that this represents some sort of a street in a city, even though the details are not really very clear. And researchers have demonstrated a similar ability to make these kinds of gist assessments from visualizations. So I can quickly compare which of two charts, for example, exhibit higher mean with respect to this sort of hypothetical variable z, or which visualization might reflect less clustering and higher dispersion. And these judgments can be made with very fast-acting visual processes that we are almost unaware of. Does this ability translate to more complex visualizations like scalar fields? And if so, how reliable are people at estimating features like summary features such as the mean or the variance in data sets like these? So to try to answer these questions, we designed an experiment where we've shown participants a pair of scalar fields at a time, and we were asking them to choose the field that exhibits higher variance. I'm sorry, higher mean. So that would be this visualization in this case. Now, the challenge with this task is that we only expose the visualizations for a second and a half, essentially to try to force participants to come to these quick summary percepts rather than attending to individual features within the visualization. Now, in addition to the mean, we also tested their ability to detect the field with a higher variance, and similarly in a second and a half exposure. In both cases, we were presenting these visualizations as if they were terrain, and we're asking folks to pick the one with the more varied terrain or with the higher terrain on average. So we have two summary statistics, the mean and the standard deviation as representing the variance. And we also tested four color maps that represent different levels of hue variation, all the way from a monochromatic grayscale to a colorful rainbow, to see if color map would impact the judgments in these tasks. Now, to control the difficulty of stimuli, we start with an easy pair of images. And if participants are able to guess correctly, then we would make the next stimulus more difficult. And we would keep doing this up to a point where people can't distinguish the difference between the two. And then at that level, we would reverse and we would make the next stimulus easier. And what this gives us is a probability of correct estimation as a function of signal strength, which is essentially the statistical difference between the two images. Now, we take these observations, we fit them to a curve. And if we take a threshold of 75% correctness, which is halfway between chance and perfect reliability, we can intersect that with a curve and we obtain what we call the just noticeable difference, or the JND, which is the amount of signal that's needed for correct discrimination at this level of 75%. So we do this for different participants and different color map combinations. And this is what the curves look like here. This is for the mean, and this one is, next one's for the standard deviation or the variance. But what I want to take a closer look at is the 75% JNDs, which are the main metric for this work. Now, for mean estimation, there doesn't seem to be a huge difference between the color maps in terms of performance here, or in terms of J&D. And really, the only small differences that we see are that we get better estimation with VIS and blue-red than we can get with a grayscale or a monochromatic RAM. And this suggests that a little bit of hue variation is useful, but maybe not as much as having a rainbow. If we look at the standard deviation, on the other hand, we see a more pronounced difference here. And here again, grayscale is the least effective, and instead we get better estimation with a multi-hue or a diverging or even a rainbow scale. The most pronounced sort of effect that we see in this study is that it's much easier to estimate the mean than it is to estimate the variance. And particularly that you need about 3 times the amount of signal to estimate variance at a similar accuracy levels. So overall, the main takeaways is that we found that people can quickly judge the mean and to a lesser extent the variance of color-coded fields. And interestingly, this estimation appears to be driven by hue features. So things like hotspots, valleys that you see in the field, more than it depends on the luminance of these representations. But as it seems, only a little bit of hue variation is enough, so you don't need to go all the way to a rainbow, for example. And this is corroborated by a qualitative analysis of responses. So if you're interested, please do consult the paper. In terms of future work, we would love to explore other spatial statistics, things like autocorrelation, skewness, anisotropy. And we can use similar methods to study those, and that in turn would give us a sort of a more holistic pictures of how people read the gist of these visualizations, and how we might be able to use them in a science communication context more effectively. And with that, I'd like to thank you all, and I would be happy to take any questions.
Great, thank you. Okay, I don't currently see any questions on Slido, so I'll ask one of my own. So in your experiment, so participants seem to rely on different visual features like the peaks or the valleys when estimating in the tasks, right? So do you think they reflect the differing levels of the cognitive load that the color maps themselves have intrinsically? And how might that trade off with accuracy?
Yeah, I think it was, if you wanted to make these estimates, you are going to be looking for, especially if you're making them quickly, you're probably going to look for specific visual features to be able to estimate at a glance. And as it seems, the peaks and the valleys were the features that people honed onto to be able to make these estimates about the mean and the variance, which sort of makes sense, right? If you're trying to estimate the mean, then you maybe would look for the highest amount of red, for example, in the image, and that would indicate that there's generally higher values in one image over the other. The variance was a little bit more complicated, where people were, I think, were looking at multiple features, so the values and also the hotspots, but also color patches and how many sort of like color contours that you might be able to get with different color maps. Yeah, so I think it probably reflects a need to make these quick judgments, but also, you know, from a vision science point of view, there are some visual features that we can process very quickly, and that's what people need to be doing in tasks like these.
Okay, cool, great, thank you.
Thanks so much.
All right, moving on to our next presentation, towards equality approach to hierarchical color maps presented by Tobias.
Thank you very much. Sharing. Okay. Now, which of these 3 color map variants is the best? As is often the case, the answer depends on the application scenario, and thus we need proper guidelines to help us answer such questions. Within the color map literature, we can find many such guidelines and design rules to inform us in our color map design process. But there are no explicit design rules for hierarchical color maps yet, even though the challenges from representing the structure of a hierarchy with colors differs from representing tabular data. And to address this challenge, we selected 6 of the most prevalent design rules for tabular data and translated them to the context of hierarchical data. To start off this translation, we interpret the hierarchical structure as two-dimensional. The vertical dimension spans the hierarchy's depth, and it is quantitative and discrete. The horizontal dimension spans the nodes on each individual hierarchy level, and it is categorical, but it contains groups of related elements, the siblings. Most color map generation algorithms then generate their colors in the HCl color space, where chroma and luminance are used as the primary discriminators for the vertical dimension, and the hue is used as primary discriminator for the horizontal dimension. This basic approach is in line with the best practices from the color map literature for such dimensions. But within this approach, there are still a number of design trade-offs to consider. So let's look at an example scenario, considering just the three design rules: device independence, discriminative power, and background sensitivity. The device independence design rule states that we should also always sample colors from within a standardized cross-device gamut, such as sRGB. Sampling colors outside of such a gamut would then lead to these colors possibly being clamped to an individual device's gamut, and that would in turn result in inconsistent color representation across different devices, and it can also decrease our color map quality in terms of the other design rules. So it's always a good idea to keep device independence in mind. But for most devices, the gamut has a very irregular shape. So our maximum chroma that we can use, meaning the circle with the largest radius that fits into the gamut, is dependent on the luminance for the given hierarchy level. And because of the irregularity of this shape, this dependency is highly nonlinear. Next, the discriminative power is probably the most prevalent design rule of them all. It basically states that we should sample colors that are perceptually as far apart as possible so that we can easily discriminate between them. To easily improve our discriminative power for the vertical dimension, we just need to maximize our sampling ranges for chroma and luminance. And for the horizontal dimension, we should use the maximum chroma possible for a given hierarchy level, because this increases the radius of the circle from which we sample the colors. But we can already see some conflicting criteria here. If our maximum chroma that we can use depends on the luminance, we cannot maximize both sampling ranges at the same time. And also, if we want to use the maximum chroma for a given hierarchy level, for example, the leaf level of the hierarchy, because that's usually the level with the most nodes on it, then we also need an appropriate luminance value for that level. Just to save you some time, the maximum circle that you can fit into sRGB has a luminance value of about 76 and a chroma of about 59. So we might think we could just set our leaf level values to these, and then towards the root node of the hierarchy, we just decrease these values, so we get a larger range than if we were to increase them up to 100. So let's just say we go all the way to 0. In theory, this should generate a good color map for these two design rules, but there's more to consider. So let's look at the background sensitivity, for example. The background sensitivity states that we should always guarantee a good contrast to the background. And because usually our backgrounds are either white or black, this contrast is mostly given by the luminance. So this places an additional constraints on our luminance range. And sadly, our good configuration from earlier, this falls apart here, because a luminance value of 76 achieves a very poor contrast against a white background. So we as designers, we need to be able to determine which design rules are most important for our application scenario and how to find a suitable trade-off between them. And to ease this decision, we introduced the concept of the analysis focus, where in top-down analysis scenarios, we focus on comparing groups, meaning the top levels of the hierarchy, such as the results from a hierarchical clustering, where we want to compare the clusters, and the hierarchy enables us to drill down into the data to find a suitable level of granularity. In bottom-up scenarios, on the other hand, we want to compare the leaves of the hierarchy. This is often encountered when we want to compare items that are hierarchically related in a non-hierarchical visualization. And the hierarchy here serves as contextual information for the analysis. So knowing this analysis focus, this helps us prioritize the different design rules and helps us find a suitable trade-off. And with this knowledge, we can move towards a quality approach to hierarchical color maps. In addition to further explanations in the paper, we also provide a cheat sheet of all conflicting criteria that we could identify in the supplementary material. So if you're interested, have a look at the paper or talk to me on Discord. Thank you very much.
Great, thank you. Let me see. Okay, I don't see anything on Slido yet. Okay, so I guess like one question that I would have is, while your paper focuses on general hierarchical data, how do you foresee your findings extending to specialized domains like genomics or social network analysis, where the hierarchical relationships also carry like a specific semantic weight associated with them?
Okay, interesting question. I could think that maybe in such cases that especially certain hues can carry different meanings, for example. That's always the case if semantics come into it. And then we would have additional constraints, basically, that we would need to incorporate into our color map design. And these, again, these are additional constraints that we need to trade off with the constraints that I identified in the paper.
Great, thank you. Cool. Moving on to our next presentation, assessing the graphical perception of image embedding models using channel effectiveness, presented by Soohyun.
Okay, can you hear me?
Yeah.
Okay, thank you for introducing me. Okay, then let me start my presentation. Hello everyone, my name is Soohyun Lee from Seoul National University, Korea. And today I will present our work on assessing the graphical perception of image embedding models, focusing on their effectiveness in perceiving visual channels. Various AI models have been developed to understanding charts, most notably for tasks like question answering and chart captioning. Although current benchmarks measure how well models answer the question or how well they extract the caption of the chart. While there are benchmarks to evaluate the performance of these models, they often focus on high-level tasks, such as accuracy in reading numerical data. These alone, though, do not provide an assessment of how well does the model see graph like human. That is, we need to assess how the model perceives fundamental graphical elements at a more human-like perceptual level. So we want to understand how models perceive chart at a perceptual level, such as how well they interpret visual elements called channels, which control the appearance of marks and visualizations. Instead of focusing on high-level tasks like question answering or chart captioning, we examine graphical perception at a low level, specifically how well this model captures graphical information at a graph embedding stage. Before we get into how we calculate the channel effectiveness of model, let me first briefly explain about channel efficiency. So for human channel effectiveness, we mainly consider four major metrics: accuracy, discriminability, separability, and pop-out. However, for the scope of the study, we focus on just accuracy and discriminability because we haven't yet found a way to explore the relationship between separability and visual pop-out for each channel when the models look at the graph. So this is for our future work, I guess. So I'll explain the first two effectiveness above, accuracy and discriminability, in more detail. First, accuracy is that how precisely can we tell difference between encoded items? So like accuracy when asking the question, if the length of the line segment above is 1, what is the length below? So we can easily estimate that the length below is about 3. This is about the accuracy of the channel length. So for humans, the accuracy of channel perception follows a specific order, as has been shown by several previous studies. Position is the easiest for us to perceive, followed by length, tilt, area, and so on. Next, discriminability is that how well we can distinguish between small variation in a channel. So for example, on the left is an example of how the gray levels become almost indistinguishable when set to 10 bits. And the picture on the right is an example of the discriminability for line width on a map. When we divide the line width into 3 parts, we can see that there is a good distinction between them, the thin one and the middle one and the thick one. So in this study, we developed a framework that evaluates an accuracy and discriminability of image embedding models. Our framework using 6 specific channels: length, tilt, area, curvature, color luminance, and color saturation, which can be easily applied to line segments. By gradually increasing the intensity of each channel, we can measure how the model's perception changes. To calculate the accuracy of image embedding model, we measure how the distribution of embedding points change as we increase the intensity of each channel. Ideally, if the model is perceiving a channel accurately, the embedding point should form a linear progression, as shown in this example. So we calculated linearity to evaluate the accuracy of the model. To evaluate discriminability, we measure a distance between embedding points. Because if the points cluster into distinct groups, it means the model is effectively distinguishing between different intensities. In the example shown in the length channel, we can find like 3 distinct groups, and it can be interpreted that the model recognizes length information by broadly classifying it into 3 categories. We tested our framework using the image embedding generated by image encoder of the CLIP model from OpenAI, which is well known for its strong performance. This approach provides us with several interesting results. First, for channel accuracy, as I said before, people see channels more accurately in top-to-down order. But the result, we can see that the order of the length, tilt, and color luminance is the same as the humans, but the accuracy for color saturation and curvature is higher than we expected. If we are say to that model looks similar to the human, the graph must have the following form. That is, in order to match the viewing order of each channel, similar to how human sees it, the channel accuracy for the length, tilt, and color luminance above must be improved. So this is about our future work that I will explain later. Moving on to channel discriminability. CLIP displays strong discriminability for the length and the tilt channel. For length channel, we can identify 4 distinct peaks, each peak at a quarter intervals. This suggests that model divide the length into 4 major steps. For tilt, the model demonstrated 2 primary peaks, centered around 0 and 45 and 90 degrees, suggesting that CLIP is good at distinguishing angles between over 45 degrees and under 45 degrees, and can also say model might oversimplify middle range angles. However, for other channels, we noticed that distance drops after a certain threshold, but we did not have any specific interpretation. In conclusion, our framework evaluates the graphical perception of image embedding models and demonstrates that CLIP does not perceive visual channels in the same way that humans do. This highlights the potential risk when using models like CLIP for tasks that require precise graphical perception, such as chart understanding or like visual data interpretation. For future work, we plan to extend this framework to include other elements of channel effectiveness, such as separability and pop-out, and future investigate perceptual metrics like J and D. We also aim to validate the finding with human studies to establish a ground truth for human graphical perception and try to fine-tune some models to follow them. Thank you for listening, and please feel free to ask any question or sharing feedbacks.
Thank you. So I see a few questions on Slido. So, okay. I'm curious about other foundation models' graphical perception. For example, do you have any plan or idea to assess the perception of multimodal LLMs?
Multimodal. Actually, multimodal LLM is in the high level tasks, such as I explained in this slide. So it focuses on such as numerical accuracy, so in a high level task. So we target to the image embedding model because every multimodal LLMs that uses vision, such as vision models, use the graph embedding embeddings. So we think that we need to we think that we need to so the embedding space need to reflect the accuracy of the channels or the discriminability of the channel. So I am not aiming to that multimodal LLM things, but I think the study will help them to improve such as the more human-like models.
Great, thank you. I think we have time for one more question. So, are there any channel combinations that might impact model performance? How do you evaluate one channel's effect influencing the perception of another channel?
So I actually in this study we tested in the single channels, such as just line width, just the length, or just color. But I think it's not fair to test that way. So in this graph that I explained is the channel accuracy for all combinations. So if we check the accuracy in the lengths, we check all the intensity of the tilt and color luminance, concentration, and curvature. So I think this kind of for all combination accuracy is the fairest part. So is it? Did I answer correctly?
Yeah, I think that was quite reasonable, yes. I think like maybe some statistical methods that compare more explicitly might also help you like inform exactly what the effects are.
Yes.
Great, thank you so much.
Thank you.
Yeah, moving on to our next presentation. So connections beyond data, exploring homophily with visualizations, presented by Poorna.
Thanks, Sanjana. Me. Okay. Hello, everyone. My name is Poorna Talkad Sukumar, and sorry, just a second. Yeah. And I'll be presenting our work titled Connections Beyond Data, Exploring Homophily with Visualizations. This work was done in collaboration with Maurizio Porfiri and Oded at New York University. So last year, I attended this conference for the prevention of firearm-related harms, where I came across this research, which shows that the race of victims in mass shootings can significantly influence public opinion and gun policy responses. Specifically, they found that mass shootings that involve predominantly white victims lead to significantly more restrictive gun laws, while those involving predominantly minority victims have much less impact. And this got us thinking, do people respond more strongly to data that reflects their own racial identity? And does this translate to visualizations? So we asked, when viewing visualizations that highlight the race of mass shooting victims, how does concordance between the viewer's race and the highlighted race influence changes in their emotional responses and attitudes towards gun control? In other words, we wanted to examine homophily in visualizations. Homophily is defined as the tendency for individuals to associate with others who share similar characteristics, such as beliefs, attitudes, or demographic traits. And in our study, we were particularly interested in studying racial homophily, which is the specific tendency for individuals to associate with others who share the same racial or ethnic background. And studying homophily can help us see how these shared characteristics, such as race or ideology, influence how people interpret visual data. And to explore homophily in visualizations, we conducted a pre-registered crowdsourced experiment. We designed 3 conditions, each condition consisting of a bar chart, as you can see here, showing the victim counts or the number of victims in mass shootings in the United States between 2013 to 2023. And we also highlight the number of white victims, Hispanic victims, as well as Black victims, respectively, in the 3 conditions. And because the number of victims varied across the 3 racial groups, we also indicated the expected victim counts in the visualization based on the respective racial groups' proportion in the US population to provide adequate context for interpretation. And those are the dotted lines here. And for each of the three conditions, we assigned 75 participants who identified with the same racial group highlighted in the visualization, and 75 participants who identified with a different racial group. And this setup allowed us to compare reactions when participants viewed data about their own race versus a different race. And our experiment had the following stages. We first collected demographic information, and then we asked participants about their views on gun control and also measured their emotional state. We measured affect or valence or emotion using the self-assessment mannequin scale. Then they viewed the visualization, one of the visualization conditions for at least 30 seconds and answered factual questions. Afterwards, they answered a verification question, followed by us asking them their emotional state and their views on gun control again. And we also asked open-ended questions and finally collected information about their political beliefs. And so here are the results. We calculated changes in emotional responses or change in valence as the difference between post-condition valence and pre-condition valence. And contrary to our expectations, we did not find a significant effect of racial concordance on changes in affect. That is, no significant differences in affect changes were observed between participants who viewed data about their own race and those who viewed data about a different race for each condition. However, across all conditions in participant assignments, we found significant differences between the pre-condition effect and the post-condition effect, with post-condition effect being consistently lower than pre-condition effect. And this suggests that the emotional impact of mass shooting data is so overwhelming that it probably overrides any racial homophily that we expected to see. And we again measured changes in attitude as the difference between post-condition attitude and pre-condition attitude. And again, contrary to our expectations, we did not find any differences, significant differences in changes in attitude between participants who viewed data about their own race and those who viewed data about a different race for each condition. And overall, we observed very minimal changes in attitude, as you can see here. And we also performed a multiple linear regression to examine the effects of age, gender, education level, political views, and racial concordance on changes in emotional responses. And the only significant predictor was political views. So participants with more liberal views had stronger negative reactions to the visualizations. And this study is a preliminary exploration of homophily in visualizations, but there's more work to be done. First, homophily effects may be subtle, so we need larger sample size studies to detect these subtle effects. And second, political ideology played a major role in shaping responses. So future studies should include more details and gather finer controls and gather should include more detailed controls and gather finer details about participants' prior beliefs. And lastly, while we used bar charts and we focused on mass shootings, future work should explore different types of visualizations and topics to understand homophily in other contexts. And with this, I end my presentation, and I thank you all for your time, and I'm happy to take questions.
Great, thank you. Okay, I don't see anything on Slido currently. I like this topic a lot. This topic is like something that I've also been like doing research in recently. So I guess my question to you is like, could you elaborate on what the different visualization types you might use would be? Would it be distributional charts, isotypes, for like more nuanced responses?
Yes, so I think there's been a study by Cindy, who's also here, which say that, I mean, bar charts actually hide like within group variability. So charts that show like individual data might be something we might consider using next. So yeah, that would include even isotypes and other charts too.
And would you consider like maybe looking at facial expression analysis or some other form of real-time sentiment tracking to explore like subtle changes in variation?
Yes, sure, that would be useful, but that would require completely different methodology. Like we would have to do in-person studies and consider participant sizes accordingly and so on, as opposed to doing crowdsourced studies.
Great, thank you.
Thank you.
Moving on to our next presentation. It's a literature-based visualization task taxonomy for Gantt charts presented by Sarvghad.
Hello and welcome everyone. My name is Saif. I'm a PhD student at the University of Utah. Today, I'm going to talk about our short paper titled A Literature-Based Visualization Task Taxonomy for Gantt Charts. So this is a joint work with my advisor, Kate Isaacs. Let me first tell you about the basics of Gantt chart. Gantt charts are generally used to visualize temporal discrete event sequences with dependencies. Typically here, data is organized by temporal order in one axis, and in the vertical direction, different events are grouped together and presented on different tracks. Here, the tracks could be different people or their role on a project or different resources like CPUs or GPUs in parallel computing. Here, rectangular boxes are used to represent different events. Also, dependencies between the events are represented with different arrows. For example, an event starts after another event finishes. These charts are highly used in project planning, resource scheduling in product manufacturing, progress tracking of computer program execution, or tracking disease progression or treatment response across different people in healthcare system. Many of these applications, especially those coming from automated processes such as manufacturing and computing, can generate data with billions of events across tens of thousands of independent tracks. This is beyond most typical Gantt chart implementations and leads to some other issues like overcluttering the visual interface, and individual events become harder to identify. Furthermore, poor support for scale becomes a significant barrier. Querying these large-scale datasets using existing techniques leads to larger visual latencies. This hampers user experience in using Gantt charts. Because of these two problems, designing a Gantt chart becomes harder. Therefore, to balance this concern and to guide people in designing Gantt charts, we decided to look into the literature to understand about the visual design of Gantt charts and try to identify relevant data queries to support different interactions on that visual design. Here, I list all the visualization tasks that we classified from the literature, and these are the data queries that we identified. This heat map shows the relationship between these queries and the visualization tasks. And also this shows the number of papers in which we observed these tasks. Our taxonomy helps by guiding the design of Gantt charts to effectively support large number of event visualization and interactions, aligning visual tasks with appropriate data management techniques. This also helps in identifying which query to implement that can support most visualization tasks. For example, to implement this visualization task like displaying full Gantt, displaying a window, and so on, we map this visualization task to this specific query called get data from a range. So if you like optimize this specific range, this would support this specific visualization task. And from here, we can see that like displaying full Gantt, this specific task appeared in 20 papers on our literature search. Using a qualitative analysis on our surveyed paper, we classified the visualization tasks for Gantt chart into 8 broader categories, and in total, 29 visualization tasks. Let's look into some examples related to some of these classified tasks. For example, the visualization task displaying event attributes. In the literature, we notice that this has been done mostly by implementing a mouse hover action on the Gantt bars, followed by showing a pop-up window. In some cases, a dedicated window is used to show the event attributes. In this case, you can see an event is being selected on the left which is highlighted using a yellow box. And on the right, the event attributes are displayed using a separate window. Okay, then let me show you another example with another visualization task, which is displaying track details. Typically, this is done by showing text for each detail. In this example, like individual people are being mapped to each individual track. That's why you can see different people named in the left and different numerical values are displayed on the right in each track. In some cases, we also notice the use of annotation in displaying track detail. In this case, you can see image of individual people has been used in each track. In some of the papers during our reviews, we noticed color encoding is used to display the track details. Here you can see each individual tracks are encoded with different colors. Also, collapsible and expandable rows are utilized to display additional track details. In cases with higher number of tracks, similar tracks are grouped together and collapsed under a single track. Furthermore, displaying highlighting techniques, different highlighting techniques are used to show different additional track details. In this case, you can see that similar Gantt bars around a specific timeline are aggregated into larger bars. Tasks that immediately follow that timeline are highlighted with saturated colors. Additionally, a track focus lens is used. In this case, when a user clicks on an aggregated bar, a track focus lens appears to display which Gantt bars are being aggregated. Okay, now let's think about you completed designing a Gantt chart. Now you want to do the implementation on loading the data to visualize it. So for this task T14, displaying track details, you would need to implement and optimize this query that we call get track details. Like this, our multi-layer visualization task taxonomy provides a structured way to guide users in designing interactive Gantt charts that can handle a large number of data. Using this taxonomy, it helps to identify which queries are needed to optimize to support certain visualization tasks for Gantt charts and their common auxiliary views. To support these diverse visualization tasks, we need a stronger data management mechanism for Gantt charts to facilitate visual interactivity. With this, I'm finishing my talk. So I'll be graduating in spring 2025. I'm also in the job market right now. So please check my CV by scanning the QR code in the right. And thank you all for your time and attention. And with that, I'm now happy to take any questions.
Great, thank you. Okay, so I guess I'll just ask a question of mine. So given your taxonomy's like emphasis on having like auxiliary views, how do you think the integration of multiple views in general impacts the cognitive load for users? Like, is there a threshold where you think having just too many views in the dashboard will reduce the effectiveness of that primary Gantt chart in the first place?
Okay, so like in this case, like our taxonomy actually like focused on like whenever you use like Gantt chart as like a primary view and also like use other kinds of like additional views, for example, like node link diagrams or other kinds of view as an auxiliary view. So our like tasks are primarily focused on this task, like whenever you interact over the like Gantt chart. So this would help you to like identify which individual task you would like choose or select. So yeah. So I didn't hear your second question. So could you say that again?
So like, is there a threshold where you think like a certain number of views is just going to like reduce the association of that primary chart being the Gantt chart that they look at in the dashboard?
Okay, so like additional threshold, you mean like how many like visualization that this can like support? Is that it?
Yeah, like how many views would you consider as like a threshold? So maybe if there are like 3 other charts that go along with the Gantt chart to explain what's happening, would that be just like for you to focus on the Gantt chart?
Yep. Actually, yeah. So actually, we didn't like focus on that. So this is mostly focused on like whenever you use like Gantt chart as like a primary view. Okay. So there could be like some other additional views that you could interact with, but all of our task is like focused on like whenever you interact over the Gantt view only. Like,
okay. Great,
I think that clears your question, right?
Yeah. Great, thank
Okay.
you. I see a couple of other questions on Slido, so I guess we can continue that discussion on Discord now.
Okay,
Thank
of
you.
course. Yeah. Thank you.
Okay, moving on to our next presentation. A zoomable level of detailed chart tables for interpreting probabilistic model outputs for reactionary train delays, presented by Aiden.
Good morning. So as you've heard, I will talk about a zoomable level of detail chart tables for interpreting Monte Carlo style stochastic model outputs. So first of all, I want to say to tell you what a zoomable level of detail chart tables are. So they are standard case by variable tables where each row is a case. In this case, it's a train, and each column is a variable. And these variables are composite metrics. They're complex metrics, which we represent with little mini charts that are embedded in the cell. The charts have different levels of detail. And when you zoom the table, you can zoom out and see how, for a sorted column, how the distribution of cases. And if you zoom right in, you'll see the glyphs changing to a more detailed version of the glyph. So that's just how they work. Just to give some context, so the reason we were working on this was because we were interested in assessing timetable robustness. So that is a sensitivity of train timetables to delays. And an important factor is knock-on delays. That is, if a train gets held up at this station here because perhaps of passenger overcrowding, and it gets held up there, then it may delay trains further up the line, and it may even delay trains further up from that. So you often get cascading reactionary delay or knock-on delays, and these can have quite unpredictable consequences on overall delay. And we were interested in finding timetables that are vulnerable to that or not. And this problem is especially common when the network is very highly loaded. It's working at capacity. So our approach to look at this was to do some agent-based modeling. So what we do is we simulate the movement of trains on the network. And this is according to the timetable. And when delays occur, the model will delay trains, and any interactions of trains will be modeled and will end up with the actual times that they arrive in this model. It's a Monte Carlo simulation, so we run the model multiple times, each of which generates a kind of alternative day. And in each day, we insert random primary delays, which are based on historical distributions, and then we get a distribution of alternative days. So here in this graphic here, if we a primary delay here in the model, this is showing knock-on delays up the network. And with all this data, we can summarize it in different ways. And for this talk, we're going to summarize them by train. So for each train, we are computing composite metrics that capture different aspects of delay. And then we have our two levels of detail of chart. The low level of detail, we just use the median across all the simulated days. And for high levels of detail, we show the whole distribution across all simulated days. And examples of the metrics we compute could be things like the amount of primary delay or knock-on delay suffered by a train, the amount of primary delay or knock-on delay caused to a train, which trains suffered the delay and by how much, and also looking at how the lateness varies throughout the journey of a train. So each of these composite metric types needs an appropriate chart design. So for the simplest one, which is a lateness chart, we have one lateness value for every simulation. So it might be a number of minutes. And in the low level of detail chart, we represent that with a median and a interquartile range. At a high level of detail, we show each value as a point and the median. So these 5 rows are equivalent to these 5 rows, but in the high level of detail version. For the lateness time profile chart, here our metric is a list of time-stamped latenesses. So these are latenesses at different stops during a train's journey. In the low level of detail version, we have a heat map for each train, which shows us the median delay by time step, where red is late and blue is early, so it's a diverging color scale. And in the high level of detail graphic, we have a separate line for each train using transparency, which shows us which parts of the profile are consistent between model runs and which parts are not consistent, where some days the delays are much, much higher. And then for the affected trains chart, the metric here is a list of train IDs with the amount of delay that was either suffered or caused by that train, depending on the metric. In the low level of detail chart, this is shown as a stacked bar graph, where every bar is a train and the length of the bar is the amount of delay that was caused the train or that train caused. In the high level of detail version, we have a bar for each of the simulations. So we have 100 simulations here. And where the hues are consistent, that means that it's the same train that was affected on multiple days. And where the hues are less consistent, it means that different trains were affected on different days, suggesting that the network is vulnerable to some chaos in the way that the trains run. So here we've got a chart table where if we look at the third train here, so they're sorted by knock-on delay. The third train, that delay was caused by one train, because we only have one bar there, and it affected one of the train, but not very much on average. If we look at the second train, so here, the lateness profile, you'll see that about halfway through its journey, it gets later. If we now zoom in and see the detail of the graphics, then we can see, for example, the second train, which we saw became late halfway through its journey. In the second half of its journey, it's actually a wide variation in latenesses, so that the lateness is consistent for the first half of the journey, and then it's a wide range of lateness. So the median tells you something, but it doesn't capture the variation within that. So some reflections. The feedback was very good. So the analysts that we worked with liked being able to identify problematic trains, and they really liked seeing the variation within the dates, because some trains are always late and some trains are sometimes late, and sometimes when they're late, it could be a catastrophic lateness. And the fact that this is modeled means that they could try different timetables and look at which timetable was more robust to that. And they also liked the fact that we could look at the effects of trains on each other. So what key trains were that caused lots of delay that we wanted to focus on. The technique is generalizable, so we can use different cases. So we used trains in this case, but you could, in fact, we did use location in a different table, and that meant that each row was a station, and we were calculating metrics on the delay characteristics of a station. We can also flexibly add new metrics by adding new columns to the table. We can design new chart types depending on composite or complex metrics, and each of those can have different level of detail variance. We could also apply this not just to Monte Carlo model result data, but to any data that has an aggregated versus disaggregated form. You could use this approach. And you could also come up with more levels of detail if the glyphs can be presented at different levels of detail. So that's my conclusion, and I'd be happy to take any questions if there are any.
Great, thank you. Okay, so yeah, I think I'll just ask a question of my own. We're probably getting it delayed from Silo. So I guess one question would be that the operating companies kind of seem partly interested in like operational use cases, but also in strategic insights. So how would you adapt your tool to better serve long-term strategic goals, like say network resilience planning?
Good question. So I haven't really thought about that, but I would think that you could do things like look at the effect of adding a new piece of track, or adding an extra direction on a track, or making a bridge wider. So looking at the bottlenecks in the network and seeing what effect that would have and how many more trains you could run as a result of network upgrades.
Okay, great. Thank you. So moving on to the last presentation, grid lines mitigate sign illusion in line charts, presented by Cindy.
Hi, everyone. Hope that you can see my screen. Thank you for joining our session. So I'll just jump right in. So our visual perceptual system is very powerful, as many of our previous talk has pointed out. But this powerful visual system that we have is trained to make sense of the natural world. So when we use the same visual system to make sense of an artificial world of data visualizations, our visual system can make mistakes because the visualizations we create to communicate data tend to look drastically different from the real world around us. So let's look at this example. So I here have the revenue of two products, A and B, and the x-axis shows time. And my question for you is, when is there a bigger difference in revenue between A and B? Here's the data. And before I reveal the answer, maybe write it down so you can't change it later. All right, that should be enough time. So moment of truth. Here's the difference between the two products at time 1 in comparison to their deltas at time 2. And you can see the difference at time 2 is much bigger. But my prediction is that all of us, myself included, saw the difference to be bigger at time 1. So this illusion is called the sign illusion. It happens because our visual system likes to estimate the difference by looking at the shortest distance between 2 points. And our visual system does this because it's used to doing this in the real world. So imagine you're sitting by the beach at the trade winds and you want to get into the water, right? And this is how you're going to go. And nobody is going to do this, right? Because in the real world, nobody cares about some arbitrary vertical distance between 2 points. We want the shortest distance. And we only need to look at this weird vertical distance in the artificial world because our visual system isn't trained in on that. What our visual system is trained in is that when we see two lines with some space between them, we want to perceive it as a shape. And our visual system wants to know how wide it is and how long it is. So we look for the major axis and the minor axis because those measurements don't change even when the object changes its perspective to you or when you move your head. Okay, so our visual system is used to doing this in the real world. And when we ask it to do this in the artificial world of data visualizations, which our visual system is not familiar with, it's going to make mistakes. So to empirically test this, we showed people visualizations like this, except that we simplified it to look like this. And we asked our participants to determine at which time 1 or time 2, the delta between the two lines is bigger. So we vary the deltas between time 1 and time 2 by systematically manipulating the slope of these line segments. So I'll demonstrate it here. So I have the ratio between the deltas at time 1 and the delta at time 2 plotted on this x-axis. And for the specific one that you see on the screen, the ratio is about 0.7. And we can manipulate the slope to change the ratio, and this one right now is about 0.5. Okay. And to make sure people don't figure out that time 2 is always bigger, we also snuck in some conditions where time 2 is actually smaller. So these are more like sanity check conditions. I won't dwell on these too much. For today, I will only focus on the conditions where time 1 is actually smaller than time 2, but you have this illusion that the difference at time 1 is bigger. So that totals some 1,638 charts in a very long within subject study that we conducted. And we also mirrored the chart so it's not always showing a positive slope. So to show you some results, like I said, I'm going to plot the time 1, time 2 ratio on the x-axis. On the left, it means that the time 1 delta is much smaller than the time 2 delta. On the right, it means that time 1 delta is more similar to time 2 delta. And I'm going to plot their mean accuracy on the y-axis. And the mean accuracy here refers to people's performance on this difference comparison task. So in this case, if they said time 2 for when was there a bigger difference in revenue between the two lines, they will be correct. So here's the result. So what we're seeing here is that the mean accuracy gets lower as the delta at time 1 and time 2 becomes more similar. When the ratio between the delta at time 1 and time 2 is about 0.7, people's performance drop below chance. They make the sign illusion mistake. So the takeaway is that the sign illusion gets exacerbated when the difference between the two deltas fall under 30%. And we can test our hypothesis to see if people are comparing some orthogonal distance in this task where they're using shape perception to draw major axes as if they're seeing shapes. So we tested several ways to formalize this orthogonal distance. And today I will share the best performing model with you. So we call this the equal triangle model. So how it works is that we assume people would choose the delta for this task, which is the dashed line you see here, by identifying some isosceles triangle from the line at time 1 and then connecting the endpoints. So taking that distance as the delta at time 1, and they would do the same for delta at time 2. We'll plot the data in the same way, except that instead of mean accuracy on the y-axis here, we will measure the accuracy by defining correct as if they had chosen the model delta instead of the true delta, just to note them here. Okay, so if people are relying on the model delta, the orthogonal, their accuracy would be high under this equal triangle model. If they're not, their accuracy would be low. So this is what we see when we recoded the data. If we assume that participants are relying on the model delta rather than the true delta, you see that their accuracy increases significantly. It doesn't fall below chance anymore. So this is suggesting that people are relying on a type of orthogonal distance when comparing the deltas. And I want to end the talk with how do we get people to not do this, right? We tried a few things. So first, we wondered if we can break this shape perception by breaking the line segments. So instead of having solid lines, we swapped them with dotted lines. And here are the results. So it looks like this manipulation has only made accuracy worse, and people are even more so relying on the shape heuristics to complete this task. So let's forget about that, and we'll restart from here. How do we get people to not make the sign illusion mistake? We tried adding grid lines to explicitly guide people towards the vertical distance comparison. And here are the results. So on the left here, we see that adding grid lines will raise the threshold for people falling below chance for this task. So in a way, it's mitigating the sign illusion. And on the right, what we're seeing is that when people are looking at the grid lines, their behavior is no longer well predicted by this equal triangle model, which means they're not relying on this orthogonal distance to make their judgments as much anymore. So to summarize, the sign illusion, it gets exacerbated when the difference between two deltas fall under 30%, and adding grid lines can help. So before we part ways, now that you're aware of this sign illusion, here's another demo for you. And this might be a good opportunity for you to take a screenshot to later impress your friends or fool your enemies. Are the deltas between the two lines here changing or constant? And here's your answer. With that, thank you all, and I'm ready to take questions.
Great, thank you. Okay, I see a question on Slido. Are there visualization types other than line charts where users could be misled by the sign illusion?
Yeah, I can imagine any visualization that includes comparison of deltas as part of its visual encoding, like area chart or streamline graphs can induce this kind of bias. And I think it's been demonstrated that when people are just comparing distances, we use this shape perception heuristic. So the answer is yes, and there are tools out there that people have developed to help mitigate this kind of illusion. And now that we know more about the kind of mathematical underlying of how slopes work together to create this illusion, we can create even more reactive tool to mitigate this. Thank you for the question.
Thank you. Yeah, I think we have time to squeeze in one more question, which is mine. So you tested the two models on the participants' behavior, right? So some prior work has shown that certain populations have lower susceptibility to visual illusions that rely on these kinds of geometric cues. So the Mueller-Lyer illusion is one, where certain like tribal populations were found to have like resilience to that. So do you think, for example, say Arabic readers would rely on perpendicular non-equal or the equal triangle heuristic in the same way?
I don't have the empirical data to justify what I'm gonna say, but I'm going to speculate. I'm gonna say I don't think so, because I suspect this illusion is driven by this shape perception where you have a major and a minor axis, and as long as people are able to perceive shape and have object permanence in the real world, I suspect that their visual system will default to keeping those aspect ratio in this shape, and then they will intuitively go for one of these axes, whether that's the major or the minor axes, like you were saying, might depend on cultural or individual differences. So that's to be investigated, but I suspect they'll still exhibit some kind of biases.
Okay, great. Thank you.
Thank you for the question.
Cool. And that puts us right on time to wrap up. So thank you all for the thought-provoking work that you've presented today. And thank you to the audience as well for having like a great discussion. Thank you.